So this section here is looking at how we use the second derivatives and what the second derivative actually represents. So first of all, what is the first derivative, dy by dx? That represents, we know, the gradient. Gradient dy by dx, in other words, you can think about it as the rate of change of y with respect to x. That's what dy by dx means. How does y change with x? If y is increasing, the difference in y is increasing with respect to x, it's said to be a positive gradient. Okay, but as x increases, if the difference in y is reducing, then it's said to be a negative gradient. So then what does d2y by dx squared, i.e. the second derivative, represent? It represents the rate of change of the gradient. Okay, so dy by dx, rate of change of y with x, and d2y by dx squared is the rate of change of gradient with x. So how does the gradient change? If the gradient is increasing, as we increase the values of x, then d2y by dx squared will be positive, i.e. the rate of change of the gradient is increasing, therefore d2y by dx squared should be positive. The rate of change of gradient is positive. Likewise, if the gradient is decreasing, then the rate of change of the gradient will be negative. Look at this little curve here and understand what's happening. First of all, gradient is represented by tangents, small tangents at each point. So if I drew a tangent here, if I drew another tangent here, if I drew another tangent here, what do you notice about the gradient at each of those points? What's happening to them? It's changing, but how is it changing? Is the gradient increasing or decreasing? It's decreasing, as we can see from the slope of the tangents. It's going from positive towards 0 towards becoming negative. So it's becoming more and more negative. It's reducing. So what can we then say about the rate of change of the gradient here? What can we say about d2y by dx squared for this section all the way up to here? It's negative, because the gradient is becoming less and less. It's becoming more and more negative. So here we expect d2y by dx squared to be less than 0. What about this bit here? What's happening to the gradient from there? What can we say is happening to the gradient for those parts? It's increasing. It's going from a more negative, it becomes 0, and then it starts becoming more and more positive. So here, for this section from there to there, d2y by dx squared, i.e. the rate of change of the gradient, is positive. Positive is indicated by saying it's greater than 0. Now, that interval, well, what is that interval? Well, we need to know what this point is. Suppose this is the point where, I don't know, it might have an x value of, let's just say, x1, y1. Then we can say that d2y by dx squared is less than 0 for x is less than x1. It's not always less than 0, is it? Is the second derivative always 0? No, it's only for a given section of the graph. So you would never just write down d2y by dx squared is less than 0. You would have to specify which part of the curve that case is true for. Which part of the curve is the rate of change of the gradient negative? It's only negative up until that point, which I've denoted using x1. So I'm saying for x is less than x1, it will be negative. For x is greater than x1, the second derivative will be positive, i.e. the rate of change of the gradient is increasing, therefore positive. So we need to indicate the range of values of x for which this second derivative is true. Now, these sections where the second derivative is less than 0 and greater than 0, we give them a mathematical name for that part of the curve. So this part of the curve where it's less than 0 is called a concave. The curve is said to be concave for that part. And the curve for this part is said to be convex. So we've got concave and convex. A way to remember it is the concave, as you can see, it looks like a cave that you're going into. So it's that kind of parabola. It looks like a cave, a tunnel. Yeah, so that's a way to remember which one is which. So don't get them mixed up. So if that's concave, the other one will be convex. So that's kind of understanding how we refer to different parts of the curve, and we can say it's convex, concave, and so on. But this point here in the middle, at that point, what's happening is the curve starts going from concave to convex, that particular point. And this point here is referred to as the point of inflection, where the curve changes from being concave to convex, i.e. where the curve starts, where the second derivative is equal to 0. Because it goes, look at that, our second derivative is less than 0. It starts indicating that the rate of change of the gradient is reducing, negative, until it hits 0 here, and then it starts becoming positive. So at that point, at the point of inflection, the gradient, the rate of change of the gradient is 0, i.e. the gradient is not changing at that point. Momentarily, it is kind of constant. Therefore, there is no change in the gradient. And that's why d2y by dx squared, the second derivative at the point of inflection, is equal to 0. So, in order to determine a point of inflection, we need to first of all show that the second derivative is equal to 0. But then we need to show that just before that point of inflection and just after it, the second derivative d2y by dx squared is going to be negative on one side and positive on the other side. It could be positive and negative or negative and positive. It really depends on which way the shape is going, whether it's going from concave to convex as we have, or is it going from convex to concave. The most important thing to show is that the sign of the second derivative changes from positive to negative or the other way around, indicating that it's gone from concave to convex, indicating therefore that there is a point of inflection in between those 2 points that you use. So suppose we knew the value of this to be x1, what would we substitute into d2y by dx squared? A small difference lower than x1. Take away 0.01 or something like that, or add 0.01 to check on the right hand side.